Thank you very much, and it's great to be here. This is an outline of my talk. I'll start with getting back to the future and explain what advances we've made in the last 10 years, and then explain some of the ideas that we recently have. Quite a bit of that were inspired by Stamatis. And there's a long list of acknowledgement, and I'm not going through that. As we all know, that the future of computing is a topic very close to Stamatis' heart. And what I also learned from Stamatis is that the future should also be exciting. We should not go for a boring future. We all know that. Especially if you have lots of students that one would want to inspire. So what would be exciting? Well, two of the most important topics are how can we optimize for future architectures, how to make them more efficient in power and in speed and so on. And then the other very important topic is that, well, when we optimize the systems, we need to make sure that they still behave in the way that we expect them to behave, okay? So we need to verify them. And what can be more exciting that couldn't we get the systems to optimize themselves and hopefully also verify themselves so that we could just sit back and say, okay, that seems like a good idea. And we could focus on how to optimize the process of self-optimization and self-verification, and we could be hopefully more productive. So this is what we talked about 10 years ago. And over those years, I had the great fortune of working with one of the greatest giants of computer architecture who isn't here today, Professor Mike Flynn, and I spent some time on sabbatical at Stanford. And we worked together on these ideas, and he also come up with ideas of having an autonomous system on chip and with networks of them, which could be very interestingly based on these ideas. And we even published a textbook on system on chip, and it's been translated into Portuguese and Chinese. But although it might increase the number by 10 times, you don't expect to be rich because the price is also reduced by 10 times as well. Okay, so what would the architecture look like? What would be the simplest way of self-optimizing and self-verifying systems look like? Well, I guess if you just put two boxes saying that these are the self-optimizing and self-verifying units, can't really get simpler than that. Now, in addition to that, of course, when we optimize and we verify, we are doing that with a reference to various models of the inputs and outputs, and also the internal states as well as the environment. So the model themselves might also be updatable in order to be most general. Now, of course, if we just have these boxes, then you might say, well, we still don't know what they are. So the insight that we got in the last 10 years is that for the self-optimization, some of the ideas in incremental machine learning seem promising. And for the self-verification, again, some of the current ideas in circuit assertions, which correspond to high performance, low overhead monitoring, would become promising. And it seems that these ideas are reasonably general so that they will cover both large-scale, high-performance data center computing as well as embedded systems. So just a very quick slide on custom computing that we know traditionally. When we compile a program, we use tools like compilers and so on to massage the program so that it will fit on a fixed processor, which does not change. But in custom computing, we could actually fit the processor because it consists reconfigurable elements so that we could now customize not just the software, but also the hardware as well to the high-level description. So the basis of this technology, as we all know, is based on field programmable gate arrays, and essentially is a array of elements such as the function of each element as well as the interconnection and the memory blocks on those chips as well can be reprogrammed. Now, but of course, it's just a blank chip. How can we develop efficient ways of infrastructures to compile to these very flexible chips? Well, that is the work done at Maxella that we collaborate very closely with, that if we could make use of these custom computing ideas with some of the data flow engines that they're developing, so that they put these chips together with memory onto a big system, then we obviously will get the custom data flow machines. And that has been used both a lot in our prototyping for fluid computer systems, as well actually in operation. And it is actually interesting that this is not now just an approximation of the future, but even Microsoft and Amazon are now talking about putting FPGAs in the cloud. And in particular, in the recent Amazon F1, they are actually developing systems based on Maxella's data flow engines. And that is one of the systems that we're compiling to. But in addition to the big systems and data centers and so on, we could also have examples on embedded systems. And one of the examples that we've been recently working on is a hyperspectral imaging. So when you have a satellite or a drone, you're taking pictures of the Earth and try to analyze the pictures based on the spectrum, whether from the wavelength, whether they look like what is like soil or water or vegetation and so on. Okay, so in other words, from cameras of different wavelengths and so on, which could be seen as a three-dimensional cube, we want to map that cube on a pixel or region-based process to have a pseudo-color map, and each color corresponds to a particular type of elements, which could be building or soil or water and so on. Now, of course, if we want to do it on a satellite or a drone, then in addition to the high performance that is needed, if we want to carry out this process on the systems themselves, then there are obviously a lot of power constraints. Now, but of course, the advantage is that if we do that, then we do not need to send the whole image data back to the Earth to analyze it on the big systems there. Okay, so can we actually do it in the sky? Okay, so that is an interesting challenge. Okay, so how can we do it? Well, one way is, as I mentioned, we could use some of the machine learning techniques. So there is a technique called support vector machines, but usually that is doing binary classification. So in order to do multi-class classification, we need a way to generalize the binary classification to multi-class, and that is a strategy that we adopt called one against one. So essentially, we just look at class 1 versus class 2, class 1 versus class 3, and so on. And then at the end, we do a vote to see whether the result analysis would be closest to class 1 or class 2 or class 3 for each particular given pixel in the satellite image. Okay, so you can imagine we have a binary classification, and then in order to figure out what the result would be, we use this idea of a Hamming code, which simply figure out what would be the closest of a Hamming code to particular identification of each class, and the class identification code obtained from the training process. Okay, so from training, we say, okay, class 1, the Hamming code, the code looks like that, and to compare the code from given pixel to see which one would be closest, and then we'll see what the result would be. Okay, so obviously this is a very high-level description. The details of the algorithm looks like this, and we'll see that in computing the details and the code and so on, we need to calculate the radial basis function, and that is one of the intensive step in this process. So the whole architecture looks like this, that we could parallelize the computation of these binary classifications, and then we then compute the Hamming distance, and then look at the results. And we look at now the element, each binary classified, we'll see that essentially it is computing the radial basis function in order to figure out what the result would be. So we map this process onto the Max4 data flow engine from Excella, which contain a Altera Stratix 5 chip, and we use various data sets from the public domain, and there are 224 spectral bands with 16 classes, so that means that the result should be classified into 16 different possibilities. So one could be water, one could be building, and so on. Very promisingly, it looks like the method I described to you, in comparison with some of the existing techniques, that it could achieve some good accuracy, and the resources we use on this particular FPGA is just below 90%, as you see over there. And then in terms of the runtime and energy consumption, again, you could see that the power consumption is one of the lowest. Of course, is not quite as low as the ARM chip, but if we look at the energy consumption, which, as we all know, that it takes into account both the power as well as the runtime, we could see that the FPGA implementation on the data flow engine actually use the least amount of energy among all the different implementation that we look at. Now, of course, what I just described is a system with a fixed training set. But we all know that the training set themselves might change. The satellite in different places, for example, might need different set of training data. And in fact, as the camera producing results, we could actually use the real data as training set for future as well. So how can we incrementally, how can we keep training the system? Now, so those of you who've been doing machine learning might know that for this support vector machine training, it is about equivalent to addressing a quadratic programming problem. And we know that to solve this problem, there is actually a global optimal, which is based on the Karush-Kuhn-Tucker condition. Okay, so I'm not going to go into this condition in detail, but the idea is that instead of training the system from scratch every time, what we want to do is actually just to incrementally adapt the KKT condition, because it guarantees an optimal solution, but we just update that condition from one set of training set to when new training data available, then we just update the new training in order to do that. And we map this into the hardware as well, in order to get an incremental SVM system. And this can be, again, built as a data flow architecture. And so far, our prototype implementation indicate that it could be 40 times faster than an optimized implementation in software. Okay, so much for the self-optimization. But if you want to have self-verification in the system itself, how can we do that? Okay, so one way we feel is to use this assertion idea. Now, obviously, assertions has been proposed by Alan Turing, which is a very long time ago. But the result is a little bit different, because these assertions would actually be used to generate hardware rather than just software. Okay, and we have the hardware so that it could run at the same rate as the rest of the system that is trying to monitor, and there are many kinds of assertions. It could be functional, it could be timing, but the one that I'm going to give an example for is to look at the statistics properties. Okay? So we could compute, for example, the mean and the variance at runtime in order to check whether the system is producing the appropriate results or not. So this idea is actually a project that we collaborate with Airbus because obviously they are interested in making sure that the avionics are producing the appropriate answers to make sure that the pilots and the other instruments will not get confused. So you can imagine that the yellow blocks are the standard data path elements, and then what we have are the green blocks, which correspond to the designs that will compute the assertions in order to monitor the output of the standard data path. And if there's something goes wrong, then we could reconfigure the standard data path to get the more appropriate results. So this is something that we look at, for example, in order to find the airspeed on a plane, because obviously the pilot cannot always see the ground all the time. So this is based on this sensor called the pitot tube. But when that gets frozen, then it might give the wrong answer. So what we look at is to look at the standard data path, which correspond to computing that equation to indicate what the airspeed could be. And then at the output, we could then put in the assertion elements in order to check whether the mean and the variance of the output correspond to the expected values. Now, obviously, when we monitor the output and so on, we want to make sure that the monitoring circuit themselves are not just high performance, but would use the least amount of resources. So how can we minimize the area overhead of these monitoring resources? We're doing it 2 steps. The first step is to illustrate that we could reduce from order n to order log n. Now it turns out that there is a way to optimize this assertion monitoring circuit in particular. There is this obvious description, which I put at the top there, and we could actually develop an efficient version of that, which would only use log n elements instead of order n elements. And we actually check that using an algebraic language called Ruby, based on the work of Mary Sheerin in Chalmers. But then we ask ourselves, is this the best that we could do? Can we do even better? Okay. Can we go to order 0? What does it mean by order 0? Okay. Well, it turns out that we could get something from nothing as long as you could compile for an FPGA. So what does it mean? Okay. Well, we know that actually on an FPGA is almost impossible to fill up the whole chip for any user design. So there are always some spare resources lying around. Okay. So the challenge is, can we make use of these resources which are not used by the standard data path, okay, in order to put our monitoring circuits there? So if we could do that, then this would correspond to order 0 because we are not using any resources that would be needed by the standard data path. Okay. For example, I show the picture over there. So let's say that we have some resources at the top right-hand corner, but then of course we need to connect the places in the user circuit that we need to monitor. So in other words, we'll need to provide these connections from the places in the user circuit, in the standard data path, to the monitoring circuit. In order to do that effectively, we pipeline these connections, and indeed we need to provide a new data flow, a new design flow, which is resource aware, because we need to only use resources not used by the standard data path in order to achieve this monitoring. So we find that as long as we could iteratively pipeline and route the connections, it's only spare resources, we could actually achieve this idea that we could get 0 overhead. And because we incrementally compile designs, we could at the same time reduce the compile time of building these systems as well. So we look at different architectures like a Leon 3 processor we could do 4 times faster. If we do something slightly simpler like AES designs, then we could produce designs 3 times faster and so on. Okay, so I think my time is almost up. And so current future work, well, we want to automate this approach. We look at different new applications, how to extend it to support managing these assertions and optimizations, how to unify this idea with some related work, such as self-tuning control, approximate computing, runtime reconfigurability, and so on. And we think that the most exciting thing would be to look at the possibility of prototyping next generation data centers, planes, drones, and so on. So we think that the future data flow, customized data flow machines could be very useful for future computing systems based on incremental machine learning for self-optimization and assertion-based monitoring for self-verification. And I hope that Stamatis, if he's around here, he will find this topic exciting, and I hope to come back in 10 years' time to tell him something even more exciting that we'll be able to do. Thank you very much.